In this video, we're going to be exploring polar coordinates and specifically the process of converting systems. So let's say we want to go from polar coordinates to Cartesian coordinates. Our point in the polar coordinate system would be expressed as r theta, and to convert to Cartesian coordinates, we would use the formula x is equal to r times cosine theta, and y is equal to r sine theta. And a great question that people have asked a lot is, where does this come from? It comes from basically using our unit circle and our Pythagorean identity. Okay, so let's express the point 3 4 pi thirds using Cartesian coordinates. So remember that in this situation, our first position is our r, and our second position is our theta. And hopefully that's obvious based on the presence of pi, but you notice you won't always have pi for your angle. So remembering that it goes r comma theta is actually important here. X would be equal to 3 times cosine of 4 pi thirds, and y would be equal to 3 times sine of 4 pi thirds. So think about your graph of where this point is located. 4 pi thirds would be here, just past in quad 3. You would go past your pi line by another pi thirds. And that is a 60-degree triangle. So we would have 3, cosine should be negative here, so it'll be 3 times, and it'll be the smaller one is the x-coordinate because it's a 60-degree. So 3 times negative a half, and the y value will be y 3 times negative root 3 over 2. Using my special triangles, I'm just remembering that this is a 60-degree, so this leg that gives us the y coordinate is going to be bigger, and the x leg is going to be smaller. So I get negative 3 halves and negative 3 root 3 over 2 for my x and y points. I strongly recommend drawing visuals to help you with all of these point conversions. You always want to think about what quadrant you're working in, think about the geometry, using not just blindly using those identities, but rather using your knowledge of the picture, the visual side of what we're doing. Okay, so let's take a look at converting the polar equation r equals 6 sine theta to Cartesian coordinates and describing its graph. So we just did how we do a single point, and now in this example, we're going to convert the entire equation to Cartesian coordinates. These are going to be a little bit trickier for sure. Not impossibly hard, but definitely trickier. Okay, so let's look at our identities. If x is equal to r cosine theta, I'm going to have 6 sine theta times cosine theta. And my y is equal to r sine theta. I'm going to have 6 sine theta times sine theta. So this is going to be 6 sine squared theta. So thinking about how I might do this, I want to be kind of strategic. I don't want to focus on solving for theta because it's going to give me a lot of inverse trig functions and my head's just going to start to spin. So I encourage you, if you are tempted, just get it out of your system one time, try it once, and that should be enough to keep you from wanting to do it too frequently. Whenever we're dealing with sines and cosines, I want to think about the Pythagorean identity. So I want to deal with sine squareds and cosine squareds. So my y is good. I mean, I like that I have a sine squared. I wish I could plug that into my x though, because I don't have any trig functions squared. So because I don't have any trig functions squared, what if I squared both sides? Okay, if I squared both sides, I get x squared is 36 sine squared theta cosine squared theta. And that's kind of cool because I see that this part right here that I will highlight, this part of 36 sine squared theta, is that not y squared? Is that not y squared? That's definitely 100% y squared. Okay, so I've got that portion in terms of y, but then highlighting this other part, cosine squared, I don't have that in terms of y. Like, I want to get rid of all of my thetas, and I only want to have functions of y here. So maybe there's a way I can rewrite cosine squared in terms of sine squared, right? In terms of sine squared. What if I used my Pythagorean identity to say that cosine squared is 1 minus sine squared? It definitely is. So if I rewrite this as 36 sine squared theta times 1 minus sine squared theta, now I have something that's in terms of only sine squared, and I like that. Okay, because I can view this as, if I want to see what just the sine squared part is, I can come back to my y equation and solve for just the sine squared part. So sine squared theta alone is y over 6. So now I can rewrite this part. Sine squared theta is y over 6. And I can rewrite 36 sine squared theta as y squared, which we already saw. Okay, so now I have this interesting equation. X squared is equal to y squared times 1 minus y over 6, which is okay. I mean, it is a Cartesian equation, but if we want to describe its graph, which was part of what we were asked to do here, this is not helpful. This is just like, I don't recognize what this is. So yes, it's Cartesian, but it's not necessarily easy enough to describe yet. So I'm going to do a little bit of algebra and see if I can manipulate this to get it in a format that I like. Oh, that's not y squared. Sorry, that's just y. That's just y. Just to reiterate, 36 sine squared is actually equal to not y squared at all. This was written incorrectly. This should be written as 6 times y. 6 times y. So this should be 6 times y. So I have 6y times 1 minus y over 6. Distributing that 6y, I get 6y minus y squared is equal to x squared. And thinking about circles, it's cool if I have x squared and y squared on one side and a number on the other side. And I don't know if this is going to be a circle or something else, but I want to try and think along the line. So I'll complete the square. I get x squared is equal to negative y minus 3 squared minus or plus 9. So using my completing the squares skills, if I add the y minus 3 squared to both sides, I get x squared plus y minus 3 squared equals 9. So this looks like it's going to be a circle with center 0, 3 and radius 3. Okay, so a lot of pre-calculus overhead happened here. When we completed the square, completing the square is something that I have a video on for my pre-calculus classes, and I will encourage you to definitely go back and take a look at that if completing the square is something that you're not comfortable with. If you have a different way of completing the square, please do it and make sure you're checking yourself against this to make sure you're doing it correctly. And we can always go over that more in office hours as well. And in this step, when I just recognized miraculously that it was a circle with a particular center and radius, that is just coming from a lot of experience with conic sections, which again is covered in pre-calc, and I have a video on that. So you might want to watch the complete the square video and the conic video again to refresh yourself on where that's coming from. Okay, so for our final take, here is our Cartesian equation and a description of what that would look like. To end this, let's take a look at going from Cartesian coordinates to polar coordinates. So let's say that we had a point that was xy already. It can be converted to polar coordinates using the identities r squared equals x squared plus y squared, and then tangent theta equals y over x. So if we express the point 3, 4 in polar coordinates, we have, let's look at what that point looks like in our system. 1, 2, 3, 1, 2, 3, 4. We are in quad 1. So I'm going to think about how long is the hypotenuse of the triangle that I just drew, and what is this angle? So I'll fill in that this is 3, this is 4. So to figure out our r, we can see where that r squared comes from. This is a 3, 4, 5 triangle. If you use our identity that 3 squared plus 4 squared equals r squared, you get 9 plus 16 equals r squared. So r squared equals 25 and r equals 5. Okay, and then for the angle, we're going to use that tangent of theta is equal to 4 over 3, opposite over adjacent. So tangent inverse of 4/3 is going to be theta, and then verify that we get a quad 1 angle. So our calculator is going to give us some angle that has this tangent, but it might give us a quad. When you use your calculator, it's only going to return a quad 1 or a quad 4 for tangent inverse, and you might have to manually adjust what your calculator tells you. So when I go ahead and hit tangent inverse, I need to be on the lookout to check that the angle given is in fact quad 1. So my calculator is in degree mode. It's telling me 53 degrees. If you are in, let's take a look at what that is in radians. In radians, I'm getting 0.93. And those are quad 1 values, so we're good there. And we'll just stick with degrees. Okay. So this covers the extent of going back and forth between polar and Cartesian that we will be covering, and usually what we are most focused on going from polar back to Cartesian, but both directions is always important to an extent. In the next video, we'll go ahead and jump into our study of calculus on these polar curves. I'll see you then.